ever had this feeling when you were on a train, kind of staring through the window, waiting at the station, and then you see another train passing by, and this weird sensation, you kind of feel like if you are moving, but you're not actually moving. It lasts just a sec, but it feels as if your brain couldn't tell if you're moving or not. Well, because it can't, and today I will tell you why. We used to believe that the natural state of all of the object is to rest, not to move. So, for example, if I threw this banana into space, it should stop moving, kind of by itself. But that's not true. Well, around 1600s, Galileo figured out that, well, if there is no obstacles, no air resistance, no friction, or anything that would stop an object, it should continue to move forever, with no loss in velocity. So in theory, if I threw this banana into space, it would move forever. Later, Isaac Newton added some more details into these observations and created what today is known as Newton's first law of motion. Isaac said, "An object that is at rest will remain at rest, or an object that is moving will continue to move in a straight line with constant velocity if, and only if, the net force acting on the object is zero." Well, maybe he didn't use these exact words because he created his Principia in Latin, but more or less. Anyway, okay, Isaac, what is the net force? Well, the net force is the vector sum of all forces acting on the object. What does it mean? It means that the sum of the forces depends on the directions of all of the forces acting. For example, if two forces are acting in the same direction, the net force will be bigger. But if two forces are acting in opposite directions, the net force will be smaller. Okay, so let's say that there is a banana in space. In this example, Kevin 1 pulls the banana to the left, but Kevin 2 pulls the banana to the right with the exact same force, but in the opposite direction. You can say that the two forces cancel each other out, so the net force is zero and the banana is at rest. You could add more Kevins pulling in different directions, but as long as the forces cancel each other out, the net force is still zero and the banana is still at rest. To move the banana, one of the forces would have to be unbalanced. The same rules apply when you're moving with uniform motion, so basically you're going in a straight line at constant speed. For example, let's say you're riding a bike. Or wait a sec. Let's say you're riding a bike. There are basically two major forces acting on it. The first one is the force of your legs. Well, the force which pushes you forward. The second one will be air resistance. Well, basically air resistance tries to push you back. It will act on you backwards. And when these two forces balance each other out, therefore they're equally strong, they have the same magnitude, the net force is zero. As the net force is zero, you move with uniform motion. So technically, as long as the two forces, the force of resistance and the force of your legs are equal, you should be moving forever. So basically, you can only slow down if there is some external force, like air resistance or brakes, that basically slow you down, that are stronger than the force from your legs. The same applies when you speed up. Basically, one of the force has to be greater, in this case the force from your legs. Then the net force is not zero and you can accelerate. Otherwise, if the net force is zero, you're either at rest or moving at constant velocity. Also, this tendency of an object to remain at rest or keep moving is called inertia. And sometimes the first Newton's law is called the law of inertia. And by the way, take a look how nice it is in here. Okay, but let's go back to the train situation. So basically both at rest and during the uniform motion, we don't experience acceleration. So we don't feel any net force acting on us. That's why we can't really tell the two apart. In fact, there is no single experiment that we could conduct to determine whether we are at rest or moving with constant velocity. When you're on a train that is moving with uniform motion, you experience the exact same forces as you experience when you're just waiting in a train at the train station. Okay, so why are we confused? Let's think about it. Usually, when we move, we see our surroundings changing. For example, when you're traveling by a train, you see that your view is changing. In this case, you're stationary, but your view is still changing as you see the other train, passing by. This confuses you and causes this sensation of movement even though you're not actually moving. Interesting. To put it simply, whether we are traveling at constant velocity or we are at rest depends mostly on our point of reference. What are we referring to when we are saying that we are stationary or we are moving? When you choose your points of reference close, so let's say you compare yourself to the building you're in, your city, or even the entire planet, you might think that you're stationary. But let's say you look a bit farther, like other planets, the sun, or other stars in the universe. Well, in this case, you realize that in fact you're moving. Just because of the Earth's rotation, the surface of the planet around the equator is moving at 1600 kilometers per hour. That's crazy. But it gets even crazier. On top of the rotation, Earth is revolving around the Sun, and the Sun is moving within the galaxy, and galaxies are moving between each other, and the entire universe is expanding, so it's just crazy. Everything is moving, but we just don't feel it, because our environment is moving with us. That's it for today. Thanks for watching, and stay curious. In fact, I use in fact a lot, this will go to the bloopers part, in fact.